primarily a consequence of there being these two predominant historical perspectives in regards to what that role is. The first of these two is one in which hybridization can potentially erode lineage diversification. So in this scenario, you have your two parental species which hybridize, and if selection acts against those hybrids and you can have potential genetic homogenization occurring, this can result in despeciation or the net loss of species diversity. Alternatively, a more optimistic perspective is one in which hybridization could instead generate novel genetic variation upon which selection can act. So again, in this case, you have your two parental species. These hybridize, and if circumstances are conducive to it, selection can favor these and result in the eventual production of a third novel hybrid species. So this produces this reticulate pattern. And now, studies of hybridization in the diversification process have historically been conducted at smaller taxonomic scales, typically below the level of genus. And so while this is useful and will give us some understanding of what the outcomes of hybridization, this typically will lack in terms of broader generality because typically evidence has been somewhat equivocal in regards to what the general process is here. And so the other side of the coin here now is that there's a general lack of macroevolutionary studies looking at the role of hybridization in this process. And so that's sort of where I'm coming from, and these are my interests. So what I'm doing here now is asking, does lineage hybridizability influence diversification dynamics? Or in other words, do hybridizing lineages diversify at different rates than do non-hybridizing lineages? So I'm gonna ask this question specifically to salamanders. By salamanders, well, nearly a third of North American species hybridize, so it's clearly a important evolutionary process that's acting in this group. And then secondly, we also have a fairly well-resolved phylogeny for these guys. This is 436 species from a Pyron and Weems tree in 2013. This was a time-calibrated amphibian tree. Just pruned the salamanders out. And then in red, you can see, that doesn't work. In red, you can see the hybridizing lineages for which we documented and delimited as being hybridizable, which we defined as the occurrence of naturally occurring hybridization. And so to then ask this question now that we've identified these hybridizing lineages, we used SSE models similar to what was discussed earlier, specifically HISI and FISI. These attempt to characterize speciation rates for a particular trait. Speciation and extinction rates, excuse me. So just to give you guys some background if you're not familiar with these, in 2007, Wayne Madison and colleagues published the BISI model. BISI is short for binary state speciation and extinction. And so what this model attempts to do is you take a binary character, which is distributed across your phylogeny. You essentially characterize the number of ways in which you have speciation and extinction events, which could produce the observed topology of your extant tree. And then you attempt to characterize speciation and extinction rates for each of those using differential equations. The downside of this is that it was found to be highly prone to false positives, specifically, again, this BISI model, the binary state speciation and extinction. And that's a consequence of two reasons. One is it's sensitive to unreplicated shifts in character state, meaning that if the trait evolved once in the tree and happened to be associated with an increased speciation rate, that can incorrectly associate it as being the driver of that. And that's related to the second issue, is that it assumes that the sampled character is wholly responsible for all observed diversification rate differences. And that might not necessarily be the case. So with that, in 2016, Bailu and Amira published the hidden state speciation and extinction model. And this now allows for the presence of some hidden or unsampled trait that could potentially influence diversification rate differences among taxa. And so this is explicitly addressing that latter of the two concerns for the BISI model. Now, in allowing for these hidden traits to exist, it allows for the implementation of non-trivial null models, specifically those that include greater rate heterogeneity to exist in the tree, and so reflect a little bit more biological realism. And so when we think about what our traits are going to be in this analysis, we have our non-hybridizing species as NH, hybridizing H, and they can either possess or lack that hidden state depending on indicated by the plus so this is what's found to outperform busy as a consequence of that fact that it includes these hidden states and thus reduces false positives. The second method we're using is this FISI, or fast intuitive state speciation and extinction. So this was very recently published by Rabowski and Goldberg in 2017, and this is a conservative likelihood-free approach that is a good complement to alternative SSC models. And so this is using this heuristic measure of diversification or speciation rate, this diversification rate, or DR, as a test statistic, and it compares this to a null distribution. DR you can think of as the rate of splitting of branches in your phylogeny of extant species. And it's important to note that this doesn't reflect extinction rates because, again, they're taking your extant phylogeny and characterizing that rate of split. So what did we find? We found, importantly, that hybridizing lineages experience a 6 times increase in speciation rate relative to those non-hybridizing taxa. FISI similarly found a positive significant result in this case. And so when we think about what we're actually looking at here, so we see the non-hybridizing species on the left, hybridizing on the right, and we see this dramatic, again, 6 times increase. And this is when the hidden state was inferred to be absent. So this we can interpret as the raw influence of hybridization on speciation rates. We similarly find this positive pattern when looking at those species inferred to possess the hidden state. So even still, here, hybridizing species have this dramatic increase in speciation rates relative to non-hybridizing. It's worth noting again that the axes here are not the same. And hybridizing species with the hidden state were inferred to have this dramatic increase in speciation rate relative to all other character states. So something's going on here. We're not entirely sure what is driving that because species were indicated to possess this hidden state and be hybridizing. So looking at this across a single axis now, what we can see are the net diversification rate, which is speciation rate minus extinction rate on the x-axis, and the probability density for the 95% confidence interval for those character states. So what we see is red and green are paired for lacking the hidden state, and you can see this positive increase. And light blue and purple are joined in that they both were inferred to possess the hidden state. And so we can see that the hidden state does appear to be increasing this speciation rate, and there seems to be some synergistic effect with the hybridizing species. But again, we're not entirely sure what this hidden state is associated with, because when we look across the entire phylogeny, what we see is that there's dramatic rate heterogeneity, and much of this is attributed to the interior of the tree being inferred to possess this hidden state. And it's pretty broadly inferred across the phylogeny, but it is concentrated within family Plethodontidae, which are the longless salamanders. But even within that group, it's unclear whether it's associated with a single trait, such as direct development or being terrestrial in nature. And this, what we see here in this density plot, are the rates that correspond to these colors, with warmer colors corresponding to the net diversification and increased net diversification rate. So what does this mean? What do we take away from this? So I've documented this pattern that is observable at the macroevolutionary scale, where hybridizing lineages experience heightened speciation rates. But it's worth noting that there's no impact on extinction rates, at least that we observed. We know that it's difficult to measure extinction rates, but across character states there was no significant difference. And so extinction rate appears to be, at the very least, constant across across salamanders. And so what could cause this? Two potential mechanisms, and we don't, with our data, have an immediate way to address this question as to what's driving this. But two potential explanations are hybrid superiority and intermediate habitat, or reinforcement, which you can think of as the strengthening of prezygotic reproductive isolation as a consequence of selection against hybrids, so hybrid inferiority. So given that case, reinforcement, for instance, could drive a wedge among diverging species and produce this pattern that we see. So I think the important takeaway, one of the important takeaways about this, is that conducting these studies at this macroevolutionary scale, looking at the role of hybridization in the diversification process, I believe is a bit more generalizable. I think it would be incredibly valuable for similar work to be conducted in other taxonomic groups to see if this pattern truly is generalizable for the tree of life, but this is at least a first step. And so again, returning to these historical perspectives, the first we think of hybridization eroding lineage diversification, where you result in despeciation. Alternatively, you can promote lineage diversification, resulting in this particular phylogeny with an increase in net species diversity. But it is important to note that we're not necessarily looking at either of these scenarios, at least as we've done so in groups such as birds, insects, butterflies, as well as plants, right? These groups for which we have well-resolved phylogenies, large phylogenies, and abundant information on hybridization. Because in order to do these sorts of analyses, we need sufficient data. And so fortunately now we live in this world where we have these large phylogenies available to us, and if not, they're becoming increasingly computationally tractable to hybrid species to, one, identify how